To find an element in an ordered array or an ordered list, we use a similar approach. So let's say we are supposed to find the number 60 in this sorted array. So we start from the midpoint of the array. That is, we find the middle index of the array. Now the array may have even number of elements, in which case we will not find the exact middle index of the array. So we can find the middle index as the max array index, which is 7, plus minimum array index, which is 0, and divide it by 2. And take the floor of the result to get an integer, because this division may give us a real number. So we get the number 3, which is the first index we look at. We check out what element is at that index and see if it is equal to the number we are searching for. In this case, 32 is less than 60. Hence, we are at least sure that if present, the number must be at the right side of the array. So we just ignore the elements which are at the left of the index 3. And now we need to find which index should we look at. So we again choose the middle index of the remaining part of the array which needs to be searched. And we can find this new index as the max index of the remaining array, which is of course 7, plus the minimum index of the remaining array, which is 3, and divide this by 2 to find the midpoint. And of course, this number may be a decimal number, hence we have to take the floor of it. And thus we get the new index again, which is 5. So we check the element at index 5, which is 55, which is less than 60. Hence, if present, the element must be on the right side. So we ignore the left half part of the array. And again find the new index using the same process. And this time the new index is 6. So we check out the element at 6, which is 60. And this is equal to the element that we are looking for. So we claim that the element is found at index 6. This type of search is called binary search, because every time we are reducing the search space by half, alright? Now this way of searching is very fast. So let's see the worst case time complexity of searching for an element through an ordered array. In the worst case, how many elements will remain in the array to be searched if the element is either found or not found? Well, every time we are reducing the search space by half, and in the worst case, we may have to keep searching until only one element is present in the search space, right? And when we check this element, the element to be searched might be equal to this element, so that the element is found, or it may not be equal, in which case the element to be searched does not exist in the array, alright? Make sure that you understand this part before proceeding. Now, in the first search step, how many elements do we have in the search space? Well, it's the whole array, right? So n elements, given that there are n elements in the array. If the element is not found when we checked the middle element of the whole array, we go to the second step, in which case we ignore one half of the array depending on which side the element to be searched might be. So in the second step, the number of elements in the search space of the array is n by 2. Then in the third step, the number of elements will be n by 4 and so on, until we reach, say, the ith step. And in the worst case, there will be only one element of the array left to be looked at, right? Now, if we look at the pattern of how the number of elements are halved in the search space with each step, that is, in step 1 there are n elements, in the second there are n by 2, then n by 2 squared, then n by 2 cubed, and so on. So in the ith step following that pattern, there should be n by 2 raised to the power of I minus 1 elements. And of course, this is equal to 1 in the worst case, right? So now all we need to do is solve this equation and get the value of I in terms of n. So I is equal to 1 plus log base 2 of n, and I also happens to be the number of steps involved in completing the binary search. So we say that the worst case time complexity for finding an element in an ordered array or list is big O of log to the base 2 of n. Now, log n algorithms are really fast algorithms, alright? And just to get an idea, take a look at this table. If there are 2 elements to be searched, log to the base 2 of n is 1. If there are about 1,000 items, log n is 10. So it takes about 10 or 11 steps to search for an item. For 1,000,000 items, it takes about 20 steps. And for 1,000,000,000,000 items, it just takes about 40 steps in the worst case to look for an item. So this is really fast algorithm, alright?